Have you ever just stopped and looked around and wondered what all this stuff is really made of? I mean, not just the chair you're sitting on, or the air, or the stars, but the actual fundamental stuff that makes up, well, everything. Today, we're going to go on a journey. We're zooming in from the world we see all the way down to the very building blocks of reality. So where do we start?
No, seriously, take a look around right now. The device you're watching this on, that cup of coffee, the very air you're breathing, it all feels so different, right? But believe it or not, underneath it all, it is all built from the exact same basic components. The big question is, what on earth are they? So over the next 5 minutes, we're going to peel back the layers of reality one by one. We'll start big and figure out what matter even is. Then, we'll zoom into the world of tiny particles. We'll learn how to sort all that matter, discover the atomic blueprint that governs everything, and finally, we'll take a journey right inside the atom itself. All right, first things first. Before we can break anything down, we have to agree on what it even is. It sounds almost silly to ask, but what is matter? You know, the scientific definition is actually super simple. Matter is just anything that has mass and takes up space. That's it. A rock, a cloud, the planet Jupiter, even the air in the room with you. If it has mass and volume, yep, it's matter. It's the stuff of the universe. Now, we usually experience this stuff in 3 familiar states. In a solid, all its basic particles are packed together super tight. In a liquid, they've got a bit more wiggle room to move around. And in a gas, they're just zipping all over the place with tons of space in between. And it turns out this arrangement is everything. It dictates how that matter behaves. And you can really see how much that particle arrangement matters right here. A solid is rigid, right? It's got a fixed shape because its particles are all locked into place. But liquids and gases, we call them fluids for a reason. Their particles can just slide right past one another, which is why they take the shape of whatever container you put them in.
Okay, so we know matter comes in different states. But what are these particles we keep mentioning? Let's zoom in one more level and find out.
For a long time, scientists were split on this. Was matter continuous, like a perfectly smooth block of wood with no gaps at all? Or was it particulate, made of tiny individual bits, kind of like a pile of sand? It actually took some pretty clever experiments to settle the debate. And when the evidence came in, it was just overwhelming. I mean, think about it. How can a couple of tiny purple crystals color 1,000 liters of water? They have to be made of something even tinier that can spread out. Or how can you dissolve a spoonful of salt in a full glass of water without it overflowing? The salt must be slipping into empty spaces between the water particles. The smell of dinner cooking wafting across the house, that tells us particles are always moving, and water forming little droplets shows that they stick together. All these clues point to one massive conclusion. Matter is made of tiny, moving particles with empty space between them. Okay, so everything is made of particles. Got it. But there's still a whole lot of different stuff out there. How do scientists even begin to organize and classify all the types of matter we see? Well, at the very top level, we can pretty much sort all matter into 2 big buckets. On one side, you have a pure substance. Think of sugar. It's made of only one type of particle. On the other side, you have a mixture, like seawater. It's got more than one pure substance all physically mixed together. In this case, water, salt, and a bunch of other stuff. And we can break down mixtures even further. If you stir salt into water, you get a homogeneous mixture. It's totally uniform. You can't see the individual bits of salt and water anymore. But if you try to mix oil and water, you get a heterogeneous mixture. You can clearly see the distinct parts. It's not uniform at all.
Now, this is where it gets really interesting, because the size of the particles in the mixture changes everything. If they're incredibly tiny, you get a true solution, and they won't settle out or even scatter light. If the particles are really big, like mud and water, they form a suspension, and they'll eventually sink to the bottom. But then there's this weird middle ground, colloids. Think milk or fog. The particles are just big enough to scatter a beam of light, that's called the Tyndall effect, but they're small enough that they stay suspended and never settle. Pretty cool, right?
So we've sorted our particles into pure things and mixed things. But what is that single, most fundamental particle of a pure substance? The answer to that question led to one of the most revolutionary ideas in all of science. You know, the idea of some ultimate uncuttable particle isn't new at all. It's been floating around for thousands of years, with ancient Indian and Greek philosophers talking about it. But for most of history, it was just an idea, a thought experiment. It wasn't until the late 1700s that scientists like Lavoisier started figuring out the actual rules for how stuff combines. And that experimental foundation is what let a man named John Dalton propose the first real scientific atomic theory. Dalton's theory was an absolute game-changer. He proposed a few simple but incredibly powerful ideas. 1. All matter is made of tiny particles called atoms. 2. He thought they were indivisible, the smallest possible thing. 3, and this is crucial, all atoms of a specific element, like, say, gold, are perfectly identical. And 4, they combine in simple, predictable ratios. This was the first time anyone had a real, testable blueprint for how chemistry works.
This was a monumental leap forward. We finally had a scientific blueprint for matter. But one of Dalton's biggest ideas was about to be put to the test. Was the atom really the end of the line? Was it truly indivisible?
All right, it's time for our final zoom in. We're going past the particle, beyond the atom, and we're going to peek at what's actually inside.
Well, it turns out Dalton was wrong about one thing. The atom isn't indivisible. It's made of even smaller, or subatomic particles. We've got the negatively charged electron found by J.J. Thomson, the positively charged proton from E. Goldstein, and the neutral neutron discovered by James Chadwick. 2 of them hang out in the center, or nucleus, while the other one zips around the outside.
So how are these little pieces arranged? Well, the first big guess came from J.J. Thomson. He imagined the atom as a plum pudding, or maybe a watermelon, a big ball of positive charge with these tiny negative electrons just dotted throughout it, making the whole thing electrically neutral. But then a physicist named Ernest Rutherford decided to test this idea. He set up an experiment where he fired tiny positive particles at an impossibly thin sheet of gold foil. He fully expected them all to just punch right through the soft pudding. But what he saw? It was so bizarre, so completely unexpected, that he later said this. You see, most of the particles did go straight through. But every once in a while, one of them would bounce right back. There was only one way that could happen. The plum pudding model had to be wrong. Rutherford realized the atom must be almost entirely empty space, with a tiny, dense, positive center, the nucleus, that contained nearly all the mass. The electrons had to be orbiting way out on the edges. But Rutherford's model had a huge, fatal flaw. According to the physics everyone knew back then, an orbiting electron should be constantly losing energy, causing it to spiral down into the nucleus. Every atom in the universe should collapse in a fraction of a second, so why don't they? The answer came from Niels Bohr. He made a wild suggestion. What if electrons aren't allowed to orbit just anywhere? What if they're stuck in special, fixed orbits or shells where for some reason they just don't lose energy? This radical idea that energy comes in these discrete levels is what finally explained why atoms are stable and, why everything exists. So, what a trip. We've journeyed from the stuff we can see and touch all the way down to the stable, subatomic guts of the atom itself. We've found the fundamental building blocks and the blueprint that holds them together. But all of this leaves us with the next giant question. How do these atoms talk to each other? How do they decide to combine and build the incredible, complex universe we see all around us? What are the rules of engagement for the building blocks of reality?